Yeah, hi, my name's Eric. I'm going to be giving you a talk about my experiences in working with etcd and building things on top of it. This is the first talk I've ever given. So yeah, a little nervous right here. Thank you. Okay, so yeah, a little bit about me. I'm a Go developer. My background, I got started as a Python developer. I was working at a biotech company. We eventually moved into Go. I was doing HPC stuff and scientific computing stuff. And a couple of years ago, I signed on with a small company based out of Vancouver and Portland called Sensu. And I've been working there ever since. And I've been working on Sensu Go there, which is an open source and commercial product for monitoring. So yeah, as I was saying before, in this talk, I want to get into a little bit about etcd. I want to get into a little bit about Raft, the distributed consensus protocol. And so at this point, you might be asking, well, like, should I be here? Like, who's this talk for? So the answer is, this talk is for people who are developers who want to know more about etcd. This talk is for operators who have to operate etcd, and you know who you are. And it's also just for people who are interested in distributed systems. So I've tried to make some content for everyone, so hopefully everybody gets something out of this. Okay, so yeah, as I said, I work for Sensu. It's a monitoring framework for heterogeneous systems. I don't want to talk too much about Sensu, but basically, you know, it's kind of the impetus for this work, and you know, it's basically a scheduler. It's a scheduler for executing host-based checks. And one of the most important features of Sensu is the ability to execute these checks in a round-robin style. So to have your workers or your agents running these things one at a time in a round-robin. So the default scheduling mode for Sensu is you know, on an interval, whether it's a time-based interval or maybe a cron schedule. Your checks are going to execute all at once across all of your agents. And depending on who you are and what your systems are like, that might be great, or it might be completely unacceptable, and it might cause a horrible sort of thundering herd scenario. So it's really important to have, you know, some way of distributing that load. So classic Sensu, the product that was developed about 8 or 9 years ago now by Sean Porter, it used RabbitMQ for facilitating that. In the new product, Sensu Go, we've done away with RabbitMQ, and I'll get to that later. So in classic Sensu, yeah, we had RabbitMQ as a broker, and RabbitMQ was basically the thing that was doing the round-robin scheduling. And basically the way it worked was that every agent would connect to the broker, it would ask for a task, and you know, that would be the you know, one message, one task sort of architecture there. But you know, it did have some issues. Like there was one Sensu backend that was responsible for, you know, consuming this stuff. And if it fell over, then there was this sort of healing protocol. I don't know how it worked, but it kind of sketched me out when I heard about it. So here's like what that used to look like. We would have a backend. It would consume some JSON documents from the file system. Things would happen. You'd get messages in RabbitMQ. They would be distributed to the agents, and then the results would be stored in Redis. And so that had a lot of problems. Well, one of the problems being that you would have to run RabbitMQ, and if you wanted high availability, you would have to run high availability RabbitMQ and high availability Redis. So we wanted to make that story easier, and we went with etcd. We ended up embedding etcd right in the product. It's a Go product. etcd is written in Go, and we had something more like this after all that. Okay, so one of the things that I wanted to make sure I didn't do this time around was follow this sort of single leader pattern where one node would be responsible for coordinating the round robin because the failure scenarios were difficult to deal with. So I wanted the scheduling to be as reliable as etcd itself and as robust as it. So I wanted to be able to tolerate the loss or failure of these nodes. And it would also be nice to have a stable order of execution for the nodes. So previously, the order of execution was basically arbitrary. It was like first come, first served. And on average, that gives you a round robin. But it's not like a nice, stable ordering. OK, so etcd, what is etcd? etcd, according to their own documentation, it's a distributed, reliable key value store for the most critical data of a distributed system, the most critical. So you're not supposed to put everything in there. We kind of did anyway, and it actually kind of worked OK, because the performance is actually really, really good. etcd is written in pure Go, so that's nice if you're writing a Go application. You don't have to worry about any Java or C components or any of the associated tooling that comes along with those ecosystems. And being that it's written in pure Go, it's easy to cross-compile to all sorts of different platforms. So if you want to run etcd on your Raspberry Pi, it actually works. So etcd uses the BoltDB database that was written mostly by Ben B. Johnson, who is a great software developer. It works really well on SSDs. It's optimized for SSDs. It can serve like hundreds of thousands of reads off of an SSD, so it does a really good job. And it uses gRPC for sending messages around. etcd is strongly consistent. At least it's supposed to be. There's a few asterisks there. I'm not going to get too much into those because mostly at this point they've been dealt with. It's been benchmarked at tens of thousands of transactions by the etcd team, also by us. I can verify that those benchmarks did seem to be true. Your etcd cluster can survive half of its members minus one. So you can, if you have a cluster of size 7, you can lose 3 machines without losing any information or losing availability. It's got a multi-version concurrency control transaction model. I'll go into that more later. You can embed it in Go applications. OK, so time to talk about Raft. How many people have heard of Raft? So like probably about a third to half of you. And then of those people, how many of you went and read the Raft paper? So like 6 people. I strongly advise having a look at that paper. It's really short and really fun to read, actually. And it's got a great little mascot. I love this mascot. OK, so Raft was created by Diego Ongaro and John Ousterhout at Stanford. And I'm really sorry to those 2 gents. I probably pronounced their names badly. Their goal was to replace Paxos, which was developed by Leslie Lamport. And the reason that they wanted to do that was because they wanted to create a distributed consensus algorithm that was more understandable and easier to implement. Raft is an algorithm for managing a replicated state machine and log. OK, so why is Raft called Raft? I actually realized this is a joke. A Raft is like logs tied together, and it's like a replicated log, like, haha, very funny Raft. Yeah, so as I said before, Raft, it's designed to maximize understandability. That's what it was optimized towards, not performance or anything else, but rather that. And it's equivalent to multi-Paxos. Does that mean anything to you or me? Well, honestly, I don't really know anything about Paxos, not to me. So Raft, like all consensus algorithms, has a heartbeat. So every node involved in the cluster is continually sending out these heartbeats to each other. And how do you know if a Raft node is alive? Well, a timeout occurs. The other ones haven't heard from it, and then they deal with it. Okay, so let's make sure we're clear on two definitions in particular, because they kind of underpin the whole thing. So what's a log? Simply a log is a data structure you can only append to the end of, other than reading it, of course. And a state machine is a mathematical model for computation. So each Raft member or node has a state machine that consumes the replicated log. And because the log in Raft is guaranteed to always be the same among its members, then the state machines will produce the same outputs, since the state machines are deterministic. So Raft members are always in one of three states. They're either in the leader state, follower state, or the candidate state. And the way that they get into these states is through elections. Elections are used to determine the leader, and therefore also the class of each member. So say you're a Raft follower, and you haven't seen a heartbeat for a long time. You will establish yourself as an election candidate and initiate an election. You'll try to become the leader. So the election process will result in a follower becoming a leader or another cluster member becoming the leader. And in the worst case, a timeout will occur, and then you'll go through the whole process over and again, hopefully establishing some sort of coherency. So this is a diagram of the replicated state machine architecture. And I essentially traced this out of the Raft paper. Sorry, Raft authors, but it was a really good diagram. So in this cluster, you've got 3 clients, and you've got 3 Raft members, servers. And the clients write to the consensus module in each server, or rather in one server, and they read from the state machine from one server. And then the servers themselves take care of, handling their own communication. So what happens is when a client wants to write something to a Raft data store, it sends, some kind of command, something like assign 4 to X. That goes into the consensus module. The consensus module confers with the other consensus modules, and at the end of that process, a log is produced, or rather appended to. So here's our log, and the log is applied to a state machine. So here we've got 4 is applied to X, 1 is applied to Y, 7 is applied to X. Okay, now we have 7 for X, 1 for Y, and Z is 0. So that's kind of the heart of this whole thing. It's not the whole thing, and there's a lot of timeouts involved in the process. A lot of very interesting, intricate details. On the Raft website, there's actually a really nice animation that I wasn't able to include in this that shows what that process looks like. Okay, so most, or even all, consensus algorithms guarantee safety. You can have network delays, network partitions, packet loss, message duplication, reordering. Almost anything can happen, in these systems. So an algorithm wouldn't be worth very much if it couldn't deal with that. So what they mean by safety is that you'll never get incorrect results. You'll never get a wrong result when you do a read from a Raft store. They're also available as long as the majority of their members are available. They don't depend on timing to ensure consistency. Rather, the timing is only for determining if their members are around and functioning. And so, like I said before, Raft has become more popular than Paxos. It's easier to understand, and it's easier to implement. The Raft paper itself says that few people understand Paxos. Even seasoned researchers have trouble understanding Paxos. I have no hope of understanding Paxos in my day-to-day job, so I haven't really tried very hard to do that. So Raft implements consensus by electing a leader. It makes the leader responsible for managing the replicated log. The leader accepts log entries from clients, replicates them to followers, and tells them when it's safe to apply the logs to their state machines. Because the leader has the responsibility for managing the log, it's free to append to the log in any way it likes. Clusters are available as long as a majority of the members are working. All Raft clusters are odd number sizes. So even if you have 4 machines involved in a Raft cluster, well, your cluster size is actually 5. So if you lost 2 of the machines in your 4-machine cluster, well, you wouldn't have an available cluster anymore. When more than half of the members fail, the cluster becomes unavailable. It's not going to service any requests until you restore enough members to that cluster to make it work again. If you have a network split, the minority becomes unavailable. And this is essential to guarantee Raft's correctness property. So one problem with the Raft algorithm is that it describes a log that grows indefinitely. And that doesn't really work so well. In a real world scenario, you can't just have your log grow forever. So there's going to be some kind of compaction that's going to happen in any real world system. And many of these systems use snapshotting or some other similar approach to deal with compaction. That's what XCD does. It takes snapshots at an interval, compacts the log, and you lose that information, but not the state. So your log entries from before just kind of get squished into one. So the key takeaways that I think are important for Raft are that if you do it right, the store will always be consistent, which is, depending on your application, hugely important or not important. It's not for all classes of applications. If more than half the cluster fails, the service goes away. And if the cluster is split in 2, the bigger half is the one that still works. OK, so I'd like to get back to etcd now. OK, so what can you get with the etcd API? Well, it's key value storage. It's not a complex database like Postgres or MySQL. You don't get SQL. You get put and get and delete. You get multi-version concurrency control, so you do get transactions. They're simple transactions where you can do things like inspect the version of a key or inspect the value of a key and compare it to something. The transactions are single round trip, so I'll get to that later. You get leases and you get watchers. I'd say those are the big 5 features that etcd gives you. OK, so here's an example of the key value system of etcd. It's really, really straightforward. You can do etcd cuddle put hello world, etcd cuddle get hello, and there's your value. And then we deleted it. In this example, we've put several keys with the same prefix. etcd lets you get a range of key value pairs. So I can get all of the cities if I ask for them. This example, it looks a little hard to understand, but it's showing the revisions and how etcd still lets you ask for older versions of keys that haven't been compacted yet. You can actually configure the compaction rate of etcd. You can configure it by time, or you can configure compaction by number of revisions. Revisions are a global counter for an etcd cluster. Every time a write is made to an etcd cluster, that revision counter increases. And you can go back and ask for old revisions of things. So more on these transactions. They're single round trip. That means that you can't read a value out of the cluster, get it back, and then write something based on that result. You only get one network round trip. So you're kind of limited in what you can do there. But you can execute comparisons server side. And there's a little example here in a Go snippet of how that kind of looks. Say you've put foo and a bar key value, and then you can say something like, well, if the value of foo equals bar, then do this put operation, set frob to true. If it's not equal, then set frob to false. So that's the kind of power of the transaction that we're talking about. It's pretty basic. Okay, so one of the more interesting features of etcd are leases. So say that you create a lease for 15 seconds, and then you assign that lease to some key. That key will be around for at least the duration of the lease, maybe a little bit longer, depending on if the cluster has time to go and delete it. So you can have a key that will expire automatically without any client control. The server takes care of it all for you. This is a photo of the Swiss Alps. It's very beautiful there. Probably one of the most beautiful places I've ever been to. And this photo is in the presentation to help us all relax just a little bit. This is another demonstration of leases. So the leases also have a keep alive feature. You can request that the cluster keeps your keys alive for a given amount of time. And I do apologize for the looping Askinema jank here. I couldn't figure out how to make them play when I clicked on them. So here we've granted a lease for 15 seconds, and we've asked for the lease to be kept alive. So that just basically involves the client sending repeated requests to the server saying, hey, please keep my lease alive unless I die, then it can go away. And so the demo here is that we'll be able to put a key with this lease and demonstrate, back to the Alps, demonstrate that even after sleeping for 15 seconds or so, that lease will still, or that key will still be around. Is it still there? Yes. Okay, so if you combine leases with their keep alives, it gives you a powerful primitive for creating database triggers. And that was something I really wanted from etcd since its transactional model was so limited. And we use leases in Sensu for implementing vigilance control, also known more colloquially as a dead man switch. So when agents haven't been heard from for a long period, a leased key expires, and that alerts the backends to the presence of failure. So leased keys can be combined with watchers for some interesting control flow constructs. So a watcher is basically something that alerts you when an operation on a key occurs. So let's say I'm watching the trees prefix here, tmuxjank, and I want to know when trees are arriving in this prefix. So from this other process, I've just got this watcher set up, and I start putting trees into the trees prefix, and the watcher gets notified every time that happens. So that's one of the, I'd say that's possibly the most useful feature that etcd gives you, other than just being able to store things in it. When you combine leases and watchers together, you can do some really cool things. How many people know what movie this meme is from? It's like 5 of you. Everybody else go talk to these people and ask them later. I've created a networking event for you. Okay, so let's make some leases and watchers together. So I've put a key, assigned it a lease, and then I can watch it to be deleted. Okay, so that's cool. So you can lease a key, you can watch for its deletion. Well, that means that you can do these kinds of triggers that I've been talking about. This is Mount Baker. I climbed up here a couple years ago in June. It was one of the coolest things I ever did. It's an easy beginning mountaineering trip. Complete non sequitur. So if you can combine leases and watchers, you can create a distributed trigger. So you can have a trigger fire on any number of clients connected to etcd. And the trigger's durable. It can survive the database going down. It can survive the clients going down. The thing is, if there's nobody watching and the database is up, then those events do just go away. So you actually do have to pay attention if you're a client. And this forms the basis of a round-robin ring. A round-robin ring is a circular list of workers. And the ring itself tracks the order that the work is going to be done in by the workers. So on a configurable interval, the workers basically travel around the ring, waiting for their turn to do something. And you may have heard of a token ring before. Unlike that, the workers themselves aren't responsible for coordinating the ring. So even if they fail, the ring itself is unimpeded, which is, I think, a pretty nice property. Okay, so this round-robin ring is operated by one or more schedulers. So any scheduler can add or remove workers from the ring. The schedulers compete to advance the ring to the next position. And so whichever scheduler actually does that advance first wins. The other schedulers say, oh, somebody did it already, I won't keep trying. And when a worker's turn to work comes up, every scheduler is notified. So it doesn't actually matter which scheduler the worker is connected to, because even if halfway through the ring triggering process, if the worker disconnects from its scheduler and connects to another one, it'll still be notified that it has work to do. So it tends to be very robust. So the workers themselves in the ring are also leased. They are leased keys. So if they don't keep checking in, then they'll be kicked out of the ring. And that keeps the work that keeps the work happening, right? If the workers go away, we don't want to have to go and administer the ring. We just want the ring to be aware of that. And we want the workers to actually, come back, re-up themselves in the ring. So etcd ranges are always lexicographically ordered. So that's also the ordering then of these rings. It's just going to be some name, like their host name, or some other name that you've given them. That'll define their ordering for work. So you can't control in this system the ordering of execution, but you can predict it. So I'm going to skip a little bit here because I've got 12 minutes. So this is a diagram of how this thing works. And let's say that the next worker to work is W2. So here we have the ring of workers, and we have the next worker, the head of the ring. And that head has a 10-second lease on it. So after 10 seconds, the key expires. It gets deleted. All of the schedulers observe that expiration, and they all go and get what the next element in the ring is going to be. And the way they do that is they just get the previous item plus the null byte, and that'll give the next one in there. They all create a lease, and then they compete to do a put. They put W3 to the next worker bucket. One of them is going to win. The other two are going to lose, and they'll just revoke their lease, clean it up. And now W3 is the next item. And that's pretty much all there is to that. It's a very simple mechanism. Even though it's a simple mechanism, I had trouble testing it. The etcd client library is hard to unit test. I tried for a long time, and I eventually gave up. The interfaces aren't easy to mock out. But I did manage to make some integration tests that run pretty fast. You can spin up an etcd instance in a Go test in like 10 seconds or less. So I would spin up an etcd instance, run my tests on it, and it seems to work well enough. You can even create multiple etcd instances in a single Go process, so it's fine. I would like to be able to do more unit testing for this. It would enable me to get way better guarantees about how things behave in weird situations, but I'm still working on it. The first time I took a stab at this, it was a complete failure. I thought I could create something that had less scheduler overhead, and it didn't work out so well. I didn't have synchronization. I didn't have that distributed trigger enabled by leases and watchers. So my schedulers were never in sync, and the thing just didn't work. So what do you have to do to test these things? You have to be able to test etcd failures, the etcd cluster. You have to be able to test scheduler failures, worker failures, or any combination of the above. So testing was very, very challenging. I basically had to just do the kind of combinatoric enumeration of these things and do my best to describe all of the failure scenarios. Okay, well, what have I learned? The feature set of etcd is really interesting. I think it's interesting, at least. And it gives you some really powerful primitives. It's also fast. But testing complex data structures and coordination routines is pretty hard. I'm still learning how to do this. If you have ideas about how to do this, please come talk to me. And expiring leases are really slow, especially in etcd 3.3 and lower. Every single one does a linear scan of the entire set of leases in the cluster, which caused some huge performance problems for me. Luckily, that's been solved. They put a heap into etcd 3.4 for these things. That was a nice surprise for me. Okay, well, why didn't you use a regular database? That is a complicated question. I was not the only person involved in picking etcd for our project. It is a good store. It's not necessarily the #1 thing I would have wanted to use. I love Postgres. I'm a Postgres guy. It's got way richer transactions, and for one thing, it's not a consensus-based system. So the throughput, in HA scenarios tends to be a lot higher. But you know what? Sometimes when you work within constraints, you can get some really interesting results. So I'm actually glad that I ended up working on etcd for so long. I think I've been working with it for about 2 years now. Okay, so why didn't you use the single leader pattern, but with etcd? I was scared that handling leader failure wouldn't work properly. I had no idea how to do it. And I was pretty sure that etcd had the primitives for building a distributed coordinated data structure, and it turns out it does. I also perceived that the single leader pattern was just not as reliable as something where all of the schedulers would contribute to coordination. And it also just seemed more fun to try something that I had never done before. Okay, so does it scale? I think it does. Sort of. So etcd, it can only do a few tens of thousands of writes per second on good hardware. etcd actually have been claiming higher numbers than that lately, but I haven't found that to be the case with reasonable sizes of key values. But what it can do is it can scale out watchers really, really well. And they've got this little utility daemon called gRPC proxy. And you can set this up in front of etcd, and you can fan out as many watchers as you like. So they benchmarked 20 gRPC proxies. They served 1 million watchers per second. And so, that means that, well, we should be able to service hundreds of scheduler nodes. Okay. And a single scheduler should be able to service thousands of workers. So, hey, that's getting up there. The ring that we wrote is open source, as well as the Sensu project is. You can have a look at it. It's under an MIT license. If anybody ever uses it, please let me know. We probably need to improve it somewhat for general use. That's my talk. Thank you for coming, and thank you for listening to me.
All right. Thank you, Eric. If there are questions for Eric, please use the microphone, or if you can't make it to the microphone, please raise your hand and I'll bring the microphone to you.
Hi.
Hi.
Have you run into any interesting operational challenges or failure scenarios in production?
Yes. Or rather, I should say, we have, and also our users have. Since Sensu is something people run on premise, we get all sorts of reports. Sometimes there's a misconfiguration. Sometimes they're trying to run etcd on spinning Rust, which just doesn't work that well. And sometimes there's some horrible problem. And what I've come to learn is that a lot of people really hate operating etcd. It's known to be difficult to operate. They recently just patched a bug, for instance, where if your client was a TLS client and it got disconnected from the cluster, the reconnection process simply didn't work. Whereas if you weren't using TLS, it did. That bug persisted for a really long time. So there have been some interesting failure scenarios. It has been challenging to work with them, but I think that these situations are becoming less common as etcd continues to become better understood by its community of developers and users.
All right. Any more questions?
Yeah, Rick Farrow. I didn't quite understand how Raft is part of etcd.
So Raft is the consensus protocol that etcd
Right.
uses.
Okay,
Yeah.
that etcd uses. Okay,
Yes.
that was the part that somehow I missed.
Okay, I'll have to
After lunch.
improve that disconnect for the next time.
Okay, thanks.
All right, great. Let's thank Eric one more time. Your first talk is over.
Thank you.